Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 6 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. Anyway, this is the problem I'm going to be going over today. We have the numbers 1, 2, 3 and so on all the way up to n written down on a whiteboard. Then every second we choose two of these numbers and call them, say, x and y. We erase those two numbers and then replace them with 2x plus 2y. So we have our n numbers on the whiteboard, and every second we're going to choose any two we want, get rid of them, and then replace them with twice their sum. Now this is continued until only one number remains on the whiteboard, and we call that number k. We want to prove that k is at least 4/9 times n cubed. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing we're going to do is state and prove a quick lemma, and that is that the square root of 2 times x plus y is bigger than or equal to the square root of x plus the square root of y, and here x and y are just non-negative real numbers. And here I've written bigger than or equal to 0. That's kind of obvious because x and y are non-negative reals, so their square roots will be non-negative reals. When you sum up two non-negative reals, you're going to get a non-negative real. Anyway, let's prove this inequality here, and it's actually quite straightforward, just essentially from the arithmetic mean, geometric mean inequality. But let's do it explicitly. Notice that this inequality here is true if and only if I just square both sides and the inequality holds true. And notice that I can square both sides and not change the sign of this inequality because everything is non-negative. So this inequality is true if and only if 2 times x plus y, which is just 2x plus 2y, is bigger than or equal to the square of this thing here, which is just x plus y plus 2 lots of the square root of xy, like so. But obviously we've got an x plus y here and a 2x and a 2y here. Let's just subtract x and subtract y from both sides. So this is true if and only if x plus y is bigger than or equal to 2 root xy. But let's just bring it onto this side here. So we get minus 2 root xy, like so. So this inequality here is true if and only if this inequality here is true. But if you have a stare at this, you might notice that this is kind of like a perfect square. This is simply the square root of x minus the square root of y all squared. So this thing here is exactly this thing here, and the easiest way to see that is just by expanding this guy here. Square root of x squared is the x, square root of, minus the square root of y squared is just y, and then when you multiply these two terms together, you're going to get a minus 2 root xy, like so. And of course we've still got our bigger than or equal to 0, but obviously this inequality here is true because root x minus root y is a real number, so when you square it, you're going to get something which is at least 0. So this inequality is true. We can track back our steps and we get that our original inequality, the one we wanted to prove, is also true. So we've proved our lemma. Let me clean up the whiteboard and we'll continue. Okay, so we've just shown that the square root of 2 times x plus y is bigger than or equal to the square root of x plus the square root of y. So what this means in our problem is, because remember we have n numbers written on the whiteboard, we take two of them, we rub them off and replace them with 2 times their sum. What that means is if at any stage, if we consider the sum of the square roots of the numbers on the whiteboard and plot that as a function of time, that's going to be a non-decreasing function. So let's kind of perhaps do a few examples just to see what that is. At the start, we have the numbers 1 through n written down. So if we just do the sum of their square roots, we get square root of 1 plus the square root of 2 plus so on, all the way up to the square root of n. But then at our first second, we're going to choose two numbers x and y from the set 1 through n. We're going to add them up. And then, we're going to rub them off and then replace them with double their sum. So then if after, say if this is t equals 0, then at t equals 1, if you write out the sum, we're going to have root 1 plus root 2 plus dot dot dot, and then at some point we're going to have root 2 times x plus y, like so, plus so on all the way up to root n. But we know that this thing here is going to be bigger than or equal to the square root of x plus the square root of y by this inequality here. So this all in all is bigger than or equal to this guy here. Let's call it S1 for the kind of score at S0, sorry, for the score at time equals 0. So we have this thing is bigger than or equal to S0, but then if we call this thing here S1, like so, we'd have S1 is bigger than or equal to S0, but similarly using the exact same argument, we get S2 is bigger than or equal to S1, and S3 is bigger than or equal to S2, and so on. So in fact, if we kind of continue this process inductively, we see that the last number we have written on the whiteboard, which is the k, so if we look at the square root of k, this thing here must be bigger than or equal to this, each of these si's, but in particular, it must be bigger than or equal to s0. So the square root of k must be bigger than or equal to the square root of 1 plus the square root of 2 plus so on, all the way up to the square root of n. So we have this inequality here. Now remember, what we want to do is show that k is bigger than or equal to 4 over 9 times n cubed. And the way we're going to do that is by having a look at this, this function here. Anyway, let me clean up the whiteboard and we'll continue. Okay, so we just showed that the square root of k is bigger than or equal to the sum from I equals 1 to n of the square root of I. But there's a really easy way we can find a lower bound to this thing here. This thing here is bigger than or equal to the sum from I equals 1 to n of now the integral from I minus 1 to I of the square root of theta d theta. And I guess one way of seeing this is just if we sketch a graph, make this our theta axis and sketch on this thing here is the square root of theta. Well, notice that between I minus 1 and I, the area under the curve, of course, is just this thing here. But this is going to be less than or equal to, well, if I just computed the area of this rectangle. So the integral of, this area under the curve is clearly going to be less than the area of the whole rectangle. And the area of the whole rectangle is simply going to be 1 times the square root of I, so it's square root of I. And of course, this area here is simply the integral from I minus 1 to I of the square root of theta d theta. So this inequality here holds. But now this square root of theta, of course, is just theta to the half. And we can just go ahead and integrate this. Very elementary integration. So the sum from I equals 1 to n of now we've got 2/3 theta to the 3 over 2. And that's evaluated from I to I minus 1 like so. But notice that this is now like a telescoping series. All the middle terms are going to cancel, so we only need to consider the last term and the first term. So the top term, when I equals n, just this top term here, this is going to be equal to 2/3 times n to the 3 over 2. And then when I equals 1, we're considering the bottom term. But of course, when I equals 1, I minus 1 is going to be 0. And when you plug that into here, you're going to get 0 to the 3 over 2. And of course, that's just 0. So all in all, we get that this whole thing here is just 2/3 times n to the 3 over 2. So we have root k is bigger than or equal to 2/3 times n to the 3 over 2. So of course, just squaring both sides gives us that k is bigger than or equal to 4 over 9 times n cubed, like so. And that's exactly what we wanted to prove. I hope that has all made sense. Thank you for watching. I'll catch you in the next one. Have a great day.